actually depict the plane by depicting a vector perpendicular to it and showing what the components of that vector are. I'm not going to do that now. I'm just telling you that's a way to do it. Don't want to confuse the issue, which is mainly that we can determine that this gives you plane. Okay? Now for homework, I'm going to ask you to try to fill in details of what I'm telling you. It's fairly intuitive, fairly obvious. You've got to learn to fill in details because that's how you do proofs. That's how you really understand something. Okay? Just knowing what happens is good. Okay? Being able to prove it is outstanding. So that's what we're aiming for. But it's not something that's immediately easy. Okay? And proofs can get very complicated and difficult. Okay? There are things that mathematicians have been trying to prove for hundreds of years. No end to the possible difficulties. There have been some interesting proofs. Like finally figured out that you can write 42 as a sum of 3 cubes. The cubes are about this long, and one of them has to be negative. Because the sum of 3 numbers, the cubes of 3 numbers this long is a number, somewhat longer, 3 times as long. Okay? So if one of them is a negative, you're not going to get 42. And that completes something that they've been trying to prove, that people have been trying to prove for 100 years. And just recently they proved it for, was it 24 or 28 or 34? I forget. I proved it in my head a long time ago, but I don't remember now which one gave me the most trouble other than 42. But there were 2 of them remaining, from 0 to 100, from 1 to 100, okay? And they proved that all of them work, but they've used like 10,000 hours of supercomputer time. The guys that proved 42 did it with a worldwide computer where people donate their computer to, you've heard of that, right? So they've seen people that agreed to have their computer used for this purpose all over the world.
The thing where
nailed it. That was really cool.
That thing where basically someone off-site uses your excess processing power.
Yeah.
Okay.
Yeah. So when your computer's idle, it uses it, and then when you start using it, it goes away. So it doesn't interfere with what you're doing. It's very cool. I should sign up for that.
I think CERN does that.
Huh?
I think CERN does that.
Can't hear it over all the noise. What?
I think CERN does that.
They probably do. A lot of people do it because it gives you, essentially a worldwide supercomputer, and that's what it takes to solve the problem. You have to have, and even at that, no supercomputer could solve it in less than 1,000 years if you didn't have a pretty good idea what numbers to look for. Numbers are just too huge. Okay? On the order of 10 to the 18th or something like that. I didn't count the digits. Just looking at it and visualizing it, maybe 18 digits, maybe more. Maybe not quite that many, close. Okay. And if you think about how big those numbers are and how big the search would have to be just to do it by brute force, even supercomputers, which are really fast, are not fast enough to handle brute force. Okay, so anyhow, it's kind of interesting. You're getting baby proofs, but they're not that baby necessarily. And any proof is not baby. Okay? Unfortunately, they don't make you do a lot of proofs in geometry class. And they don't teach you a whole lot of logic in the curriculum. Makes it a little tougher, but it's manageable. Haven't looked at yours yet, but I think it's going to be pretty good and practical. Just proving vector space properties. I think y'all are going to be fine with that, so we're going to go into proving some of this stuff because it gives you a picture of how You can take a vector space and map it to another vector space and what the possibilities are. If you go on R3 into R3, you might only get an R2, a plane in R3, okay? You could even only get a line in R3, which would be this case, okay? So you collapse all of R3 to a line, you can collapse it to a plane, or you could map it onto the whole darn space. Now, just another example. Okay, there it is. What real space does this map from, and what real space does it map to?
R3. From R3 into R2?
Yep. You just answered it. R3 to R2. It should be obvious why. I want you to kind of fill that in with a complete explanation of why, because it focuses you on the things you need to look at to understand what's going on, that you might forget to look at, so you get a proof that's obvious if you look at it right, and you sit there beating your head against the wall for years because you get stuck in a loop of not looking at it right, kind of like I do sometimes. Yeah, pretty much every day, I guess. But you get the idea, okay? So it takes vectors in R3 to vectors in R2. So let's just call this A, call this matrix A, and let's write a little notation. Okay, the transformation T from R3 to R2 is defined by matrix A by T of X, where X is a vector in R3, equals A times X, where X is a member of R3. Does that notation kind of make sense?
I don't know what the E is.
This membership, this means is a member of, is a vector within, or is a member of the space or the set R3, okay? It's a set membership. Okay? A little basic set theory wouldn't hurt you. I'll try to find a reference because you can do it in an hour.
For clarification, A with asterisks all the way across in 2 rows, would it be equal to asterisks all the way across in 2 rows with the 3rd row of zeros going across it?
No, because if it had a 3rd row, it would be mapping into R3. If it had a 3rd row, you would get 3 numbers when you multiply it by a vector in R3. Okay? In other words, A times a column of 3 numbers gives you a column of 2 numbers because there are only 2 rows. If you had a row of zeros, it would give you star star 0, which would be part of R3. Okay? So it's a good question. And it's kind of related, but you basically have an R2 within R3 if you have the row of zeros. Okay? So what could A reduce to? And what does each possibility tell you? So I'm gonna leave that as a question for you to think about. I mean, right now, so get an answer here in a few minutes, hopefully.